Thank you all very much for coming to this talk. Just a quick show of hands so I can kind of, learn a little bit about you. How many of you are working in industry? Okay, how many of you are working in academia? Okay, some overlap there, but that's okay. How many of you, need to run either A/B tests or experiments or observational studies? Okay, so cool. We'll go ahead and dive in. So I don't know how I would describe the structure of this talk. It's kind of business and then a little weirdness and then more business. It's not really a mullet. It's like a mohawk or something, but we'll dive right in. So here's a quick agenda. We'll give some context, some motivation. We will fly through the suite of R packages that the DeclareDesign project has created, and then give some takeaways and future work, and then Q&A, which is always my favorite part. So the executive summary that I always start my talks with this, which gives everything away anyway. So we're in the middle of a reproducibility crisis. So between that, budget cuts, a lot of increased competition, it's made it harder to win grants. It's made it a lot harder to demonstrate business value if you're in industry. Your stakeholders will now expect pre-analysis plans to be highly specific, so you can't just do a generic power analysis. You can't just say, okay, if I get 50 patients or 30 lab rats or whatever, everyone likes 30, right? We learned that in Intro to Stats. You can't do that anymore. You need to be a lot more specific, but simulation methods are great for pre-analysis plans. Simulations, though, are a pain. There's a lot of bookkeeping that you have to write that same code over and over again. Every rat runner's got their own specific design that they want to do. But we've written some tools called the DeclareDesign suite to make that easier for you. So I always also like to start with a quote. So this is from Bugsy Sigal. If you haven't heard of him, read his Wikipedia page. It's very colorful. But one of the things he did after he started the Flamingo Casino over in Las Vegas, he's apocryphally said to say, never put money down unless you're sure in advance you will win. And I think that that's kind of the environment a lot of data science is in right now. There was kind of a honeymoon period in the early 2010s where everyone wanted data scientists. Whether that worked or not is another question, but now people really want you to demonstrate business value, right? So we'll dive into that. So some context. So the reproducibility crisis is kind of an ongoing thing. If you read Andrew Gelman's blog, you see this pretty much every day. Such and such study failed to replicate. Maybe chocolate didn't actually make you healthier, or maybe wine didn't actually make you healthier, or maybe when you have chocolate and wine together it does. Who knows? So a couple references on that. People are still arguing how big of a deal this is, but it's definitely in the news and kind of in the air. So we'll talk a little bit more about that. But as a consequence of all these things, there's a much greater emphasis on both computational hygiene and statistical rigor. And by computational hygiene, what I mean is if you're doing your stats in Excel and there are typos in it, that is a big problem. And by statistical rigor, I mean if your analysis is doing some weird stuff, if you're shaving outliers and things like that, that could be a problem. And this is especially true in econ and the social sciences, where people are making either interesting claims about wine and chocolate or about public policy. And should we fund this program or that program? So pre-analysis plans are kind of one of the big solutions to that. I'm going to quote Olken 2015 at length because he's much more eloquent than I am. So he said, one potential solution is to pre-specify in a precise way the analysis to be run before examining the data, including everything, all of the variables, all the data cleaning procedures, your regression specifications, and so on. This is much more specific than kind of the standard power analyses that I learned, in grad school. So this isn't how many lab rats do I need. This is like the whole kitchen sink. And then he says, if the analysis are pre-specified in advance and the researchers are required to report all the results they pre-specify, then we don't have to worry about data mining. P-hacking's not really a thing then. But then there's kind of the question like, well, who is making these requirements and how far in advance? But I won't get into that. I will talk about how do you actually do it. He also mentions that pre-specifying all these things comes at a cost. It's not free. It is work. In my experience, it could be twice as much work. He says up to 30% more work, so somewhere in there. He also mentions a typical research paper is trying to elucidate or test various predictions from theory rather than estimate a single parameter with a single hypothesis test. So when you learn those power analyses, that's for one thing. If you're doing one test on your group of lab rats, that's what you can get. If you do some other stuff too, you need a more complicated power analysis, and it might not even be analytically feasible. You might need to resort to simulation methods. And then he described what Andrew Gelman calls the garden of forking paths, and this is really at the heart of it. So he says that hypotheses are often themselves conditional on realizations of other previous hypothesis tests. And pre-specifying the entire chain of logic for every possible realization is overwhelming for even the most committed pre-specifier. That's a good word, a pre-specifier. And in practice, researchers often get ideas for new hypotheses from seeing realizations of the data that they did not expect to see. And the idea, or the reason that this is called the garden of forking paths is if you do the thought experiment, you're in a garden and the paths are going every which way and you're trying to get over to the truth, there are so many paths going in so many other directions that you're never going to get there, right? And that's pretty terrifying. So now I'm going to pivot a little bit. So it turns out that Andrew Gelman did not coin the phrase the garden of forking paths. That's coming from the South American modernist Jorge Luis Borges. And so I'm going to talk about him for a little bit. So I don't know how many of you all saw Interstellar. Okay, so there was a little scene in there where they're like looking at infinity, right? And there's the library inside the library inside the library. Okay, so Interstellar also was ripping off Jorge Luis Borges, a short story called The Library of Babel, which is just a fantastic story. I would recommend all of you go out and read it, if not all of his ficciones. But it's this great thought experiment where you can imagine, all right, what is a book? It's a set of pages. What's a page? It's 80 lines with a set number of characters on it. We have 26 letters in our alphabet, maybe a space, some punctuation, a finite number of symbols, and so every single page is a combination of symbols. There is a finite amount of knowledge that can exist, right? It's an astronomically huge number, but it is finite. And Borges's thought experiment was actually, well, if we imagine a library that contained every single possible book, which contained every single possible page, inside there is, in his case, he was talking about the true word of God, but inside that library is also every single possible transcription error of that Bible. And if you're a librarian in there, there's really no way to know the difference, right? So this is a nice kind of parallel with that garden of forking paths. So if we go back to that, we can think about, okay, we have these forking paths, and it seems overwhelming, but it's only overwhelming if you're starting from scratch, and not every realization is equally likely or interesting, right? And then his second thing is about, well, if you get new ideas, well, new ideas are great. Like, write another paper. That's how you get tenure, right? But I'm going to talk about DeclareDesign now. So Borges imagined a library containing every possible book. In that library is also every realization of every possible study. And so what do those studies look like? They're like tables with some numbers in there, right? And that's how they might be encoded. And we as librarians can imagine querying the card catalog of that library, right? And so that's kind of how I think of DeclareDesign philosophically. What it does is it provides a way to specify a query which encodes the variables you want to use, the sampling strategy, your experimental assignment plan, your data cleaning, and your analysis. You package all of that up into a query and you sample back realizations of that study. Maybe one of them's the true one, probably not. You're probably not that good at specifying your study, but just that going through that exercise will really help you plan a better study. So I think of DeclareDesign as a computer scientist as a domain-specific language for doing a bunch of the stuff that, actually implements that query language. So it provides a DSL for synthetic data generation, for realistic sampling and assignment strategies, common analysis strategies that are reasonably conservative, and then just enough glue to integrate and simulate all of those together. It's fast enough for a large n of repetitions, which is pretty important. I think everything I learned in grad school about like appropriate number of simulations, you should probably 10x it or 100x it, but that's fine because computers are bigger now. And it's extensible. So we're going to dive in. So there's 4 packages in the DeclareDesign suite. There's actually a couple more that are still works in progress, but we'll start with fabricatr. Are you all familiar with cross-validated? It's the Stack Overflow for statistics. Yeah. So there's a great moderator on there, W. Hoover. He answers all the questions. Man's a saint. If you ever meet him in person, just like give him my thanks. But this is a great question on there. So the question is, how do you simulate data to be statistically significant, by Nilasha Bhattacharjee. She says, I'm in the 10th grade and I'm looking to simulate data for a machine learning science fair project, which is fantastic. When I was in 10th grade, I cared more about driver's ed. And she says, the final model will be used on patient data and will predict the correlation between certain times of the week and the effect this has on medication adherence within the data of a single patient. The adherence values will be binary, so 0 means they didn't take their medicine and 1 means they did. And she wants to include the time of the week and separate the week into 21 time slots, 3 for each day, and simulate 1,000 patients worth of data. So this is kind of the minimum number of specification in order to simulate something, right? So, you know, she asked, is there any program that can do something like this, or a Python module? I mean, you can definitely roll your own. So you can start with, you can imagine a bottom-up approach where you're going to define the compliance as a function of the subject, the week, the day, the period, and then the periods are a function of the subject, week, and the day, and on and on. So there's a lot of boilerplate. So then you think, well, I don't want to do that. We'll do the top-down approach. And then you end up doing, well, you're 5 for loops nested before you're doing anything interesting. And so fabricatr is designed to help you do this kind of thing. It's designed with, I would say, kind of 2 key ideas in mind. So the first is to generate columns that look like real data. So this might include like Likert survey responses, demographic variables, etc. And then generating rows that are structured like the real thing. So that includes panel data, multi-level or nested data, structured or cross-classified or panel data. Just a side note, so when you say you're simulating significant data, like significance is a air quote word in my opinion, but that's going to depend on several things. So the effect size that you're specifying, your sample size of your simulation, and then also luck of the draw. If you run it a couple million times, some of them are going to be significant, right? So keep that in mind. And that luck is, of course, relative to the null hypothesis or your null model. But this is what that would look like in fabricatr, and it actually fits on one screen if I make the font small. So that's great. And so what you do is you say you have a subject level. Within subjects you have week, which have days, which have time periods. And then at the very end we can say, okay, make it a probit. And it'll be a little bit higher if it's a weekday and a little bit lower if it's the weekend. Piece of cake, right? Right, so very brief introduction to fabricatr. We'll move on to randomizr. Randomizr is all about random sampling and assignment. So kind of the key thing to realize here is that your random sampling procedure is a function, right? So what that is it's a procedure that is specified, and that can be a simple random sampling procedure or complete if you, depending on how much information you have about your population. That might include strata or blocks if you're doing assignment, and it might include clusters. And you might also need the probabilities for later use if you're doing inverse probability weighting, for example. This introduces like an extra layer of bookkeeping that you have to kind of deal with depending on your analysis. It's also pretty straightforward. So if you wanted to do a cluster random assignment, hey, there's no recursion here, there's no flow control. All we've done is declared what kind of clusters we want to do. So we might want to say we have 3 clusters, 4, 4, and 7 for whatever reason. Oh, it's because we want to have extra people in the treatment group and fewer in the control and placebo. Control and placebo should be the same, but in practice, usually they're not. This is another good example of trying to do something quasi-realistic instead of just calling everything, assume IID or whatever. Also, a quick note for the people in industry. I know you're all doing simple random sampling because that's what we do extensively in online ads. We flip a coin or roll a dice or whatever. And that's very easy to understand and it's very easy to implement, which is great. But this also means that the different sizes of your groups is now a random variable. And if you actually take a step back and think about that, that has some kind of interesting implications to like, what you're actually going to get out of the experiment. In expectation, it should work out fine, but reality is often not as nice. And if we can simulate these things very much, we can identify those kind of pain points and then maybe not just do simple random sampling. Maybe we add some strata or something like that into the study. The third package I'll talk about is estimator. And it implements common analyses. So for example, difference in means or Horvitz-Thompson estimators, and then a family of regression. So robust regression, the Lin estimator, and instrumental variables using two-stage least squares. So for the means, this is very standard. If you learn the t-test, you basically learned this. It just has some bells and whistles. So if you have, for example, within blocked or clustered effects, it can take advantage of that data and get you a bit more efficient estimators. Same thing with Horvitz-Thompson. This, if you know how the randomization is being done, you can again get more efficient estimators. Same thing with regression. Again, just trying to take advantage of what the design already knows about the randomization in there. Also as a bonus, Luke put a ton of work into developing different standard errors. If you're coming from Stata land, like a lot of econ and poli-sci people are, it's very easy to swap these out. We've done a similar thing in R so that you don't need to use the sandwich package. One of the nice things is that it is 2 to 5 times faster than LM and sandwich. And so what that means is you either run bigger models for the same price, or you can run a bunch of smaller ones, or you can run a bunch of simulations. It directly integrates with randomizr so that it can, again, get more efficient estimates based on that. We have an extremely good coverage of the feature matrix. So the different estimators work with the different versions of random assignment, which work well with the different types of standard errors, etc. And it also plays nicely with TextReg and the tidyverse. So if you want to take the output of this and drop it into an iter document, you get your summary tables coming out of it quite nicely. And so then finally we get to declarer, which would have been a better name than DeclareDesign, but that's okay. And this really exists just to put those 3 components together. So our complete study has a population with parameters of interest, a sampling strategy, assignment or experimental manipulation, and outcomes that depend on it, and then an analysis which estimates those parameters. So we might say, okay, if we make the font bigger, people click more on the ads if you're in industry. And how does it work? Well, what it does is it partially evaluates the functions from all the other packages to create steps. You plus them together to create designs, and then you simulate that thousands of times with the appropriate bookkeeping, and then aggregate those simulations to make diagnostics, such as you find out your entire procedure is biased or has poor coverage, things like that. That's kind of the punchline. So each of the steps is pretty much a direct translation of calls in other packages, so I thought I would call that out. And I'm going to work through a quick example just because I think that makes it much more concrete. So this is roughly based on or inspired by the high school and beyond study that is used in every single example that the UCLA Stats Consulting website has on their page for Stata. But the short explanation is you have students nested in classes, they take a math test and a reading test. And this is a very standard design for multi-level models. So a lot of the multi-level models stuff kind of came out of that. So then a question is, so what if a teacher bought their students coffee? Well, then we might hypothesize then the students would do better. This is completely confounded with the teacher effect, and so then that teacher could get a raise if you're in the value-added teaching kind of paradigm. So, fun example. So when we're thinking about our population, we might say, okay, we've got 10 teachers. Each of them has a class size with an average of 20 students in it. The teacher has a latent ability to teach math. It might be normally distributed, and a latent ability to teach reading, which is also normally distributed. And then we have students, which are nested within or assigned to each of those teachers. We can specify this n equals class size, so the different classes might be bigger or smaller, and each student has a latent variable. We'll call it IQ. That's not particularly, politically correct anymore. I don't know. Bad example. But we can say, okay, what are we actually measuring as outcomes here? So we're in the kind of Rubin framework for thinking about potential outcomes. So we can say their test score, is kind of the sum of two things. We've got a math component with 50 questions on there. So, you know, their ability to answer correctly is some function of, I don't know, an intercept plus their IQ plus the teacher's ability to teach math. And then their reading score, which is the same thing, but we've also stuck the coffee effect in there in bold, right? And we're assigning the students coffee, and the coffee can be a 0 or 1 indicator variable. So this is a strong assumption, right? The idea that coffee only affects your reading ability but not your math, but we can simulate it. We can declare an estimand. So this is the true parameter of interest in our population. So we're interested in the true difference in test scores in our population if all of the students had coffee and if all of the students did not have coffee. And this is the average treatment effect. We can declare a sampling plan. So we can say little n number of classes are going to get coffee and then the rest won't, and we'll cluster by teacher. So the teacher is giving the entire class coffee. We can do some, that was sampling. This is assignment. Sampling and assignment look very, very similar because they're very, very similar procedures, right? So yeah, we're assigning by teacher which students get coffee. Then we can have a very basic linear estimator, your test score, what's the effect on coffee, and we're going to specify the estimand equals the ATE. That's important for the bookkeeping, but otherwise uninteresting. And then, that came out tiny. And then what we do at the very end is we just plus all of these things together, and this is our entire design that we can simulate end to end. We can do a bunch of neat stuff with designs. Once they're kind of set up, we can draw sample data out of it using the draw data function. Here we get 36 students from a couple different teachers. You can see that they have a IQ, they have a test score if they had coffee, and a test score if they didn't have coffee. And then you can see they have an actual realized test score, which, depending on if they had coffee or not, corresponds to the counterfactuals. We can simulate that entire design, which gets us a bunch of estimates of those coffee effects. So yeah, in this estimate line, we can see, oh, sometimes when you give people coffee, that's a huge effect, and sometimes it isn't. It really depends on the class. There's, you know, sampling variation in there. We can do diagnostics. I'm sorry I had to make this tiny, but yeah. If you specify 10,000 simulations, this runs 10,000 simulations, aggregates all of those and gets you some kind of higher level diagnosins about this procedure that you came up with. So the important ones are bias. So this is overestimating the effect of coffee by 0.36 questions per student. And then our power is 0.5, which is basically the same as guessing. So if we were to do this, you know, imagined coffee study, this is probably not the way to go. And also we got some timing stuff. So 10,000 simulations took about 240 CPU seconds. So now that we know this, maybe we're like, well, if we're coffee scientists, we want to do something else other than give the entire class coffee. Maybe we split the class in two and give some of them coffee and some of them not. Or maybe what we want to do is give some of them decaf and some of them regular and see if there's any differences there. Also, a really nice part about the package is that given a design, you can actually edit it and explore other counterfactuals. So we can say, redesign it, you know, try all the effect sizes between 0 and 1 for in between 2 and 10 classes. And we get our power curves. And these power curves are specific to this entire process. There is no analytic solution to come up with your power. Good luck getting G-power to do this. But here we can actually see that, you know, okay, once we're up over, I mean, even if we did all 10 classes, we're still under 80%, which is kind of the standard, but it's a lot better than being over here at 2. So there's that. You also get curves for your other diagnostics. So this is the type S error rate, which is the probability of not only getting a significant result, but in the opposite direction, which in this case would say that coffee makes people dumber. And so we can see that, you know, when for the different effect sizes, this comes down. Even if we did all 10 classes in the study, there's still about a 10% chance of this happening. And I think this is something that, you know, if you're running online ad experiments, you get a couple hundred people through the system, you know, depending on the clustering that's going on in that data, you might be over here in that 10%, you might be over here. And you don't know unless you actually go through the legwork and run the simulations. So also this is great because it's reusable. So after we've collected the real data, we can plug that back in through the exact same design to get our final results. And that's just the get estimates function. You give it the design and the actual data, and then your analysis is done. You don't actually have to do anything else at that point other than drop it into Knitter and, you know, send it to the journal. So that was all kind of an imagined example. So here's something a little more realistic. So this was an email that came into the ASA consulting mailing list. So he said, "Hello consultants, has anyone ever worked on a project where we have a pre and post group? And we know that everyone in the post group was in the pre group, but we have no way of mapping each individual's pre-response to their post response. If so, what kind of methods did you use? Would a linear mixed model with time is fixed and another grouping variable, school in this case, as random be appropriate?" So this is actually very similar to like a problem set question from Intro to Stats, which is great. All of you that can remember back that far, think about the difference in the numerator and denominator for a paired t-test and a two-sample t-test. Right? The numerators are the same, the standard errors are different. But we could, you know, simulate this, no problem. So what if we did know everything? We can just declare our population. We've got a school with some classes in it, some students, very similar to what we just did, only now we have a time dimension in there. We can add that level in, come up with some kind of score for it. And then we can declare two different estimators. We can say, okay, what if we do have the student ID variable and can track them over time? And so I'm using a mixed effect model here like he suggested, but this is also to demonstrate that you can plug in whatever estimators you want. Like Ben Bolker wrote Elmer. It's a great function. We didn't write that, but you know, our packages can definitely integrate with the rest of the modeling ecosystem that R provides. So yeah, you can just put two different estimators against the same data set into one design and then actually run them side by side and see what the difference looks like. Okay, so that was all very fast, but some takeaways. So simulations for the PAPs is feasible. You know, it's not impossible or overwhelming. It's a good way to explore trade-offs. It's a good way to try out your assumptions. And it's a good way to explore what are the consequences of violating them. So typically if there's a big effect size, then it's not so bad. And if there's not, it's bad. There's also no need to reinvent the wheel. So, you know, if you're ever doing stats consulting and people want to know how many patients do I need, how many lab rats do I need, you know, you don't have to redo that work every single time. And also this is still a work in progress, so there will probably be more features coming out sooner or later. For future work, I would call out the design library, which is a bunch of pre-rolled designs that are parameterized. So you can say, all right, I'm doing a 2-arm A/B test. You know, here is my sample sizes for each arm. Here is the effect sizes. What does this look like? Also working on fancy designs, so more complicated things. User interfaces, and I called out progress bars specifically as something I would like to have. And then visualizations of these things. For funding, we're grateful from Laura and John Arnold and EGAP for helping us build this. And then lots of people on the team. Nick, sorry. So at UCLA and poli-sci, we had Graham Blair as the PI, myself, Luke Sonnet, Aaron. We're in Columbia, we had Alex Kopic, and then Berlin had a whole group of people, McCartan Humphreys kind of managing them. And then questions. Not seeing any hands yet. So here's some rules for being a good detective. This is from Judy Moody, Girl Detective. So don't be afraid to ask for help. All of this is very confusing, and I had to kind of spend some time in it to figure out what all of this was and why it fit together. I also try to always keep a sense of humor and an open mind, and don't get in a bad mood. It can cloud your judgment and cause you to overlook important clues. Yeah?
I could talk loud enough. So I kind of giggled when you mentioned industry understands random samples. I've only worked in like Boeing, Toyota, Honda. No, they don't. And again, they got in too big into the business units to tell me enough persistence, but they've been very quaint estimates. They don't want it to be different from the last report they got. It's a little variation.
Right. So one thing that's very nice about DeclareDesign that I didn't talk about is that it bootstraps everything by default, which does make it much slower, but it also gives you error bars on every single thing. I didn't necessarily want to try and explain error bars around bias, but that is definitely something that's built into the packages, and it is great. If you're the kind of person that's developing new estimators, that can be great because then basically your simulation section is written for you. Yeah?
Speaking of the bootstrap, so when the example you gave, you were sampling from known distributions, you could just do that all day. Can you use it to get the distribution of actually already existing data? You know what I mean? Like to
Yeah. So that's a
more realistic.
yeah, that's a bit more advanced of a use case. But since DeclareDesign is implemented in a purely functional manner, you can swap out fabricate for another function in the fabricatr package that does fast resampling for you, and then you can generate it directly from an existing data set. Yeah.
I can see that being useful in industry.
Yeah.
You already have all this data.
Right. Definitely. Yeah.
I have a question about, so how extensible is it to having many variables? I work in epigenetics, and so I've written my own simulations, and I have 400,000 outcomes by like 300. So I'm just wondering how extensible is it, and is it going to be robust to that?
Yeah, so when you're starting to talk about really, really big data sets, you probably want to use a sparse representation. Would that be fair to say? So then if you go into triplet notation or long format or whatever you want to call it, yeah, you should be able to run it straight through. You might need to implement some custom wrappers for estimators to work with sparse matrices. Yeah.
Anyone else?
Okay, so a question people often ask is, do you have any resources? So DeclareDesign.org is great. Nick worked quite a lot on getting that all nicely integrated. How can you contribute? Actually, it's an open source project. It's on GitHub, so PRs and bug reports would be very welcome. What about other stats packages? This is a SatRday, so probably less of an issue. So yeah. Also, it seems slow. This is not as well advertised, but you can make it faster. You just use the future package, which we'll be hearing about later. So don't forget to turn that on. It's a great package. What kind of fancy designs did I allude to? All sorts of fancy designs. So mediation and causal analyses are very hot. Regression, discontinuity, and spillover. We already have like vignettes of how to use these things in the design library. These are some things I poked around on. They're not as fully developed, but change point detection, capture, recapture data sets are things I've worked with a lot in ad tech. And you can definitely do those kinds of analyses inside the DeclareDesign framework. Can't you just use gpower? No. So I don't know how you get the coffee variable into this thing. Good luck. Other epigraphs, so this is the more serious one that I booted from the front. So planning means both to assess the future and to make provision for it. So that's kind of what DeclareDesign is for. It lets you simulate it, and then once you know that everything will be terrible, you can do something else. All right, thank you very much.